All right, Tobias, do you want to start slowly just setting the scene? I think while people come in, we can slowly start.
I'm very happy to do so. So first of all, welcome to everyone. Thanks for joining. See that even more people are joining, so that's great. We're very, very excited to welcome you today to our first event we're actually doing of hopefully a series in the future. And it's called MLIL, or Machine Learning in Real Life. And the whole purpose of why we started this event is just that we have the pleasure, the opportunity in our daily job at Hasty to just talk to a lot of great people doing enterprise-ready AI. And there's just a lot of knowledge that's not yet transferred well and shared well. And so we want to just contribute to this exchange and have that exchange. And this is why I'm very happy that we're here today and also have the 4 amazing speakers. And yeah, and also I will stop talking now, like basically we'll get as soon as possible to the speakers, but just go through some agenda for today and some housekeeping. And then, yeah, we will get started with the talks as soon as possible and actually give the stage to the speakers, not myself. So just for the agenda today. So I think most of you saw it on the landing page when you signed up, but just as a small reminder. So now in the first 10 minutes, we will just do some housekeeping and organizational things, and we will introduce Hasty and Ignite, who are organizing the event. And we will also just say 1 or 2 words of why we're doing it, what we are doing, and how it comes that we're organizing that. But yes, as I said already with my initial moderation, we try to keep this part as short as possible to then actually give the floor to our amazing speakers. And Dr. Alexander Roth will start kicking us off. He works at Bayer Crop Sciences and will talk about their strategy and how they scaled multiple vision AI projects around the world. And he will be followed by Dr. Liana Movsesyan, sorry, I hope I pronounced it correct, from Infineon. And she will talk about how Infineon identifies our use cases and finds the right data. That will be followed by Dr. Séverine Habert from Intel, who will talk about hardware considerations when deploying AI applications. And last but not least, Julia Gong from Stanford will close that, and she will talk about her research on how to translate medical AI to rewrite. And this is the first part of the event. And I will, before each talk, also introduce the speakers a bit more, so you know, a bit more context. And then, yeah, then after that, we will have an exclusive fireside chat with the speakers for our customer advisory board. So the people who are in that all were invited. So I think you know who that is. And yeah, just stay in the call, so you don't need to do anything. And then after a short break, we will also get started with the fireside chat. And yeah, we'll give you a bit more insights and details then. And yeah, just 3 very simple things, just for like organization things. After each talk today, there will be a 5-minute Q&A. And if you have questions for the speakers, please just put your questions in the chat, and then we will go through it after the talk. And the second thing is actually that we would ask you if it's okay for you to turn on your cameras. Because we actually had the experience last week that we spoke at a conference and everyone turned off the camera, and it's not as pleasant as a speaker if you talk to back screens. And so just to make it a bit nicer for the speakers, if you are fine with it, if you can do it, would be nice if you can turn on your camera. And last but not least, we will record the session, but we will only record like the main screen, so meaning only the speakers. And your face also, when you turn on the camera, won't be in the recording unless you turn on your microphone, because then you take over the main screen. And just keep this in mind, please. And yes, this is already all the organization things. And with no further ado, I would actually hand over to Tristan to introduce Hasty. And then after that, Alois will introduce Ignite.
Can we reverse that order, please? Alois, please go first.
Okay.
Okay, you want me first?
Yes, please.
Okay, sorry. So hello, good evening, good morning for the ones who dialed in from the US. My name is Alois Eder. I'm Intel CTO for Europe in the Ignite program. Ignite, what is it? So it's Intel's startup growth program, where we invite basically 10 startups twice a year for an intense 12 weeks. And Hasty is right in the middle of that, or actually almost at the end of that. The program itself includes mentoring, expert sessions, fundraising preparation, investor, industry partner introduction. So it basically covers everything that is needed for startups in their scaling phase. And this selection, in the selection phase, when we come to this 10 startups per batch, we actually look and talk to hundreds of startups all over Europe. And we look very broad in the technologies. So basically everything from silicon manufacturing, hardware development, chip development, software, all the way up to cloud services. And what we see there is that more and more startups are using AI. Now, it's not a surprise. That's no news to you, right? So, but the numbers that we see, meanwhile, are really impressive. So roughly 50% of all startups we talk to somehow use AI in their development, in their service offering. And already 20% of the startups have really an AI-related product to offer. So this is really, really impressive. So what we see in this process is that it comes along with all the challenges of applying AI, bringing it to the market. So there's a very clear need for tools, for learning, for expert exchange also, and therefore I can just say big thanks to Hasty for organizing this event. It goes exactly in the right direction. And yeah, thanks in advance to the speakers, great speakers actually. And with this, enjoy. And over to you, Tristan.
Thank you, Alois. Thank you for that background. So as Alois mentioned, we're Hasty. I'm Tristan, one of the CEO and one of the co-founders of Hasty. We founded Hasty to get vision AI projects into production. That's our mission. We do this using agile methodologies for machine learning. We're an end-to-end solution for vision AI. If you want to find out more about it, please feel free to reach out to us. You have our email addresses in the calendar invite, and we're happy to discuss that. But this evening was not supposed to be about us. It's please supposed to be about the speakers, and it's your session. So as Tobias mentioned, please do turn your cameras on. And remember, the goal is to have an interactive session here. It's designed and guided to be a shared learning experience where we can exchange with each other. And please keep that in mind for the evening. So thank you. Without further ado, back to you, Tobias.
Yes, thanks so much, Tristan. Thanks so much, Alois. And yeah, we even had scheduled 2 minutes. Didn't expected that. No, but then yeah, without further ado, Alex, I would say you're up, and just like 3 sentences about Alex before he takes over. But who is Alex? So he works at Crop Sciences, and there he spent the last year designing and actually evolving the AI strategy. So he's actually one of the best persons probably to talk to about enterprise AI and how to get AI to the world. And yeah, he's a background in research and actually great ability to dive into technical details while keeping the big picture in mind. So it's like interesting to see what he has to say. And yeah, and today from outer space, not from a prison cell as usual, Alex Roth.
Thank you very much. Thanks very much for the introduction. So thanks for having me. I'm going to share my screen. There you go. You should be able to see my presentation. So again, thank you very much for having me, and definitely looking forward for that lively exchange here. So today I'm going to talk a little bit about challenges we had when we scaled up our AI development. Especially, like, we are definitely not talking about like doing some AI experiments, but we are talking about like having multiple AI projects, dealing with a large amount of data, couple of thousand images, for example, that we receive, and so on and so forth. Now, why is AI important for us? Like, as you probably know, there is a vision of future farming, like with the whole sophisticated technologies you have, like you have different sensors, you have different images you get, for example, from satellites, you have multiple sensors out in the field. There is a potential where you can use AI in order to support farmers, like make them more profitable, make them more efficient, or eventually help them to be more environmental friendly. And in particular, that means that we at Bayer, we work on different products to support farmers. For example, crop yield prediction, so predicting what crop outcome will be at the end of the season, or intelligent spraying, where we talk about like reducing the chemicals that actually have to be sprayed in order to reduce the overall chemical application. And what you can also use is you can use AI for a lot, for example, especially in disease diagnosis. And that's exactly where we as Bayer produce a lot of digital projects where we focus on AI as one of our main capabilities. So it's not where we just enrich products with AI, but we build products around the idea of AI. And today I actually want to talk about a little bit of some insights. What challenges we had when we scaled up, when we produced more and more AI projects, when we introduced more and more AI capabilities into our portfolio, especially for the crop protection topic. I want to talk especially about two topics. First, like how did we scale? How did we scale our data management, especially like how did we reduce the management overhead introduced when scaling data? And how did we increase our data quality and also our provisioning speed of data? And once we talk about that, there's also the need to talk about the streamline of AI development. So how did we actually enable rapid AI prototyping to spin up more and more AI projects? And how did we reduce our annotation costs and somehow introduce a loop, the data, so-called data flywheel, that is run automatically to constantly try to improve our projects? Please keep in mind that I'm going to talk about imagery data today, as there are some other challenges when you talk about other kind of data. And I know there are many, many more topics to talk about, but unfortunately I was just limited to 15 minutes only. So let's start. So when you're talking about data management, you typically end up with an architecture that's called data lake. So you start with your data lake, and there are actually different stages how you can use that data lake and to really make value of AI. Like the initial idea is like you use a data lake just as a random low cost scalable environment. You just do some experiments and you basically like keep it off of your IT landscape. It's good for small projects. We all started that way. But once you make more use of that, you actually have to integrate that. So you start doing experiments, you put just enough governance on top of that in order to make sure that you can do your 5 to 10 AI projects, and that's it. But once you start using the capabilities of AI, you actually have to think of like, how do I get all my data from data warehouses on top? How do I leverage all that, especially at scale? So you try to integrate your data lake with your internal architecture. You try to scale it. Most probably you will start with batch processing only because it's the easiest one. And on top, you put more governance. And that's still not enough because there's more to come with AI projects and more consumers on the other hand. So you go the next step. You use your data lake as your core architecture with a lot of governance on top. It's the only source of truth. You handle operational data at scale and so on and so forth. Well, that's actually the theory of a data lake. And it's actually good in practice, good in theory, but bad in practice, because you still have challenges when you continue scaling. Challenges as of like, well, who owns the data? Who cleans the data? Why is everyone actually busy cleaning the data rather than spinning off new AI projects? And these were exactly the same issues. We were actually in there, and we somehow had to think about like, hey, how do we actually continue scaling, producing more and more products, digital AI-based products, and at the same time, not reduce the overhead in order to manage all of our data? So that's actually the shift of us to switch from a data lake architecture to a so-called data mesh architecture. And it's a huge shift. The data mesh architecture means that your data is not considered as a second or third generation byproduct, whatever you name it, but it's your primary product you produce. So it's something you have in mind whenever you develop some product. And the idea is to have it as a self-service design. Our implementation looks as follows. So you have on top some kind of a some kind of a layer that's called the domain agnostic standards, where you keep your metadata, your schema definition, your policy. So everything you want to enforce on your data, so that it is interchangeable and accessible. At the bottom layer, you actually have a so-called data infrastructure as a platform, where you have standards, standardized workflows. For example, our annotation workflow that is standardized, that can be used off the shelf in order to annotate our data and produce high quality data. However, the key element of this infrastructure are so-called domains. So basically, you just simply do not put all the data in a bucket as typical in a data lake. You orient and you design your architecture based on domains. A domain, for example, has as focus to produce high quality data. For example, a domain can be a disease imagery or pest imagery in our cases. They use these domain agnostic standards and also this infrastructure to produce really high quality imagery that can be used. Just giving you an example. So when we talk about the domain is not simply just a storage of data. A domain is also responsible to develop products that are responsible for getting the data, for harvesting the data, and also responsible for cleaning the data and providing clean data to other customers. So data is kept as one of the main aspects in here. When you basically go in the other step further, you basically try to scale up, you get more and more domains. But what you actually want to do is you want to keep your data, make it accessible, and consider that data mesh as your core architecture for sharing data and for building new digital and AI-based products. So what we did is we enriched that architecture with an event sourcing system, giving you the chance to speed up the data provisioning time, so you have instant access to all of the data, and you can simply put your application, your additional application, your new application on top of that architecture as an additional domain. Interestingly, that's a topic for its own. When you talk about analytics, you actually reduce your amount of data you actually have to copy around. And so there is no potential for syncing problems, for example, you typically have when managing data. So for us, one huge learning was basically well, we still are able to scale up, and much better to scale up. We can introduce more and more domains. However, and interestingly, the team we actually have in order to manage our whole infrastructure shrunk. So we have a very small team just managing 2 layers, but we can scale up very fast and introduce new products. Additionally, we can provide data very quickly. So once data is in the data domain available, it is instantly available for any arbitrary consumer. But the very interesting effect is that data is treated as the main product in our domain. So a product owner who is responsible for a domain is also responsible to provide cleaned data for a particular domain, to develop the corresponding tools to harvest all data. However, that still helps us, when dealing with managed data. But we still, when we talk about the domain, and especially harvesting data, we still run into issues like, hey, how do we keep our data clean? And especially there are multiple use cases where we talk about apps. And when talking about apps and you work with customers, you will definitely have a lot of images or a lot of data you do not want to have. So what we actually did is, and in our layer below, we introduced AI-based filtering for each of the domains that can be shared and adapted to particular domains. And you probably know one of these filters, like image categorization, one of the easiest filters. So you basically train your model based on some predefined categories that you have, and by experience, that model filters out. Works quite good if you, for example, try to figure out images where there's a dog on top of it. It's very strong and targeted. However, the effect which you have and when using it in basically in real life, it suffers from a closed world assumption, meaning it assumes that the distribution in training set is equal to the distribution of the test set. So what happens? The performance of your model in real life basically is a bit off. So what we did is we basically introduced some other approaches. That's, for example, one of those is called out of distribution detection, where the approach is to find what actually does not fit your images. It helps overcoming the closed world assumption. However, it is not quite bound to a particular domain. So what we did in order to increase data quality, we realized AI models for both of them and run them as an ensemble with a random forest. Well, the nice effect of what we have is that once we have the data in a data domain and you run that filter on top of it, you basically get increasing result in your data quality because it performs very, very good for our use cases when we talk about domain images you want to collect that should somehow conform to a particular topic. Just to give you an example, this is one of our products that we currently have out there. It's the digital yellow drop. It's an IoT device you place in oilseed rape. It's yellow because oilseed rape is yellow, and it collects images. And next to that, we also offer a mobile app where you can go out into the field, take images, and you basically like execute the algorithm. So what it helps us introducing these filters is, on one hand side, we can filter out every arbitrary image we do not want, as we have basically the user taking that images. However, for the AI scientists among you, you will see that we still have a stationary device on the left-hand side. So we take pictures, a couple of thousand a day. But if you know AI, like, does not mean if you have similar images that it significantly improves your AI performance. So in order to see how we dealt with that, we actually have to take a look into how we streamlined our AI development. And we streamlined our AI development by exactly two aspects. Like typically when you spin off your project, you have an idea in mind that you want to create a first initial model. So for us, the goal was not to create the initial model within minutes, within months, but within minutes or within multiple days, but not weeks or months. So what we did is we streamlined everything from infrastructure provisioning, standardizing the environment, access, templates for AI, everything that is necessary in order to make an AI developer create a new project. So we can instantly spin up a new AI project and reduce the initial development time. What typically happens then is once you have your model, you're actually in the loop. Like you start with your pre-processing, with your training and optimizing and evaluating. And that's exactly the point where we try to support exactly that process by implementing it with different approaches. What I mean by that is we've implemented the flywheel, where we, for example, funnel all the data into the process, into the pre-processing, for example, the customer data. But on top of that, we actually introduce active learning. And that's exactly how we deal with the other amount of scaling data. So we use active learning to identify exactly what kind of data has the significant impact for that particular domain, or for that particular use case. And that's exactly the data that we want to have, that we want to annotate. So that way we reduce our annotation costs and also reduce the training time because we reduce the amount of data that is used for training. What we also did when scaling, and especially like when we have multiple AI projects running at the same time, you just typically go through that group over and over again, the more data you have. But we do not do that manually. We automated everything. So we automated training, we automated pre-processing, we automated hyperparameter optimization. So that basically helps us that we automatically and periodically can retrain and run through that whole loop for all of our AI projects that we have. So eventually we do that, we run through that process and figuring out what the end result is in order to see how our AI projects evolve and get better and better when we are talking about like having multiple AI projects. This definitely helped us to improve to deal with different AI projects, and especially like multiple AI projects coping with them. So if there's something actually you take away from that talk, it's basically like when you try to scale your AI projects, the key learnings is like manage your data at scale and automate as much as you can. Thank you very much. Definitely looking for the fireside chat afterwards.
Awesome. Thank you so much. Super interesting. I would wait another 20 seconds for more questions to come. If not, we have two already there, and then just getting started on that. Okay. All right, so I will start with the first one, with Tristan actually. And the question is a major learning that the combination of data and code aggravate Lehman's second law that in software entropy increases time flows? How do you structure for discipline here?
I think how do we structure for discipline? So if you're considering like organizational disciplines, so employee discipline and so on, that's definitely a topic on its own. It is definitely a challenge. However, we have a quite motivated team, and especially in the new areas, I wouldn't say it's a challenge for us right now. But we can definitely have a discussion afterwards if you experience other way.
That's very straightforward. Then I would actually jump to the next question that's coming in by Ralf Groß. And he, first of all, thanks, Alexander. But he's interested in how you identify the domains and how do you separate them?
Exactly. That's a very, very interesting. That's a very, very interesting question. So basically, to be honest with you, that's kind of a learning as we started with the data mesh, I think last year. So right now we orient our domains according to the different use cases and focuses of our projects. For example, we have a project that focuses on pests. So this will be eventually our domain. If we have use cases that target diseases will be our domain. So we build our domains around the idea of what might be the next product that we deliver to customers. So this is why we also can combine domains. Like you can use data from basically like different domains, aggregate them to form a new domain. But this is again also for us quite a learning, as we pretty much are still in the process of adapting all of our infrastructure to this data mesh.
Right, so it's actually a very nice transition to the next talk by Liana about how to find use cases, but there are more questions coming in, so I would actually spend some more time here. So the next one is from Ashutosh. I hope I pronounced it correctly. Sorry if not. But he's asking, how do you account for differences in algorithms when automating the training and hyperparameter optimization? Can this system also help automatically identify the best algorithm choice for the project?
No. So basically, that's a very good question. So the system basically automates like when you have your first idea and once you have your model up and running. So we do not automate like how to find the best model. This is something we had quite some chats with, or some ideas with, but it's kind of hard. So we currently follow the approach of like, well, we have a set of templates or predefined architectures you can try out, and you choose the ones that best fits. From there on, we basically build on top of that the automation. So it's not like we help you to identify that's the right model and you don't have to do anything. We still have that particular manual step that you have to do, because like it's still some kind of AI is still some kind of an art. So it's not something you can take off a shelf and see like, well, that's the algorithm that's worked for it. That's basically the part where we have AI scientists, you guys here.
It's interesting. It actually also touches exactly on the other question in the chat in terms of how many changes you need to make to the new template when applying it to a new use case. So it's answer the question at once. Awesome.
No, Tristan, I will not.
Right. So assuming that no more questions are coming in, thank you, Alex, for now. I'm happy to dive deeper into what you presented in the fireside chat later. And then next up is Dr. Liana Movsesyan from Infineon. And Liana is responsible for identifying and executing on viable AI use cases for Infineon. So it's a natural question to the transition to the question that came earlier. And in her talk, she will dive exactly into this, like how is Infineon identifying the new use cases. And yeah, we had a lot of interesting conversations with Liana in the past about best practices. And now I'm happy that she's sharing the wisdoms with the bigger round and not only with the Hasty team. So.
Well, it's my pleasure to be here. Thank you, Tobias. Can you please give me short feedback when you start to see my screen?
Yes, it works.
Thank you for the feedback. So hello, everyone. As Tobias mentioned, I'll share in this round today a little bit some of our experiences and learnings, how to identify viable AI use cases and where to find the right data. So I act as a interface between the AI core teams and the domains in manufacturing inside Regensburg. Maybe just for the beginning, I already predefine what I will mean as a domain in my presentation. A domain for us is an area of particular process during chip manufacturing. So it's just an area which has a particular expertise and knowledge about the processes and the data related to these processes and equipments. Just, yeah, so short a note. But maybe it will be helpful first to understand how the semiconductor manufacturing ticks. And for that, just a little bit fact sheet about Infineon, which main business is focused to produce semiconductor chips for different applications, mainly in segments for automotive, industrial power control, power and sensor systems, as well as connected secure systems. The company has several development sites and 21 manufacturing locations across the world. I particularly work for AI focused on manufacturing, but I will in my talk introduce a little bit how in general, in which areas in general we tackle problems with AI. So what is it all about, AI? What has AI to do with Infineon? Yeah. So on one hand, the products that Infineon manufactures can get smarter in the way that we, for example, include AI into the devices. Imagine for your automotive applications, your radar systems on your cars are way smarter and can very well orient them in the different circumstances in the streets. Or imagine you need to have already some AI logic in your products so that you can smartly monitor the data that the sensors are collecting. So in case of field applications, you can very quickly come to realization that something is going wrong before any fault happens. So on one hand, with the products, Infineon can enable AI, but for its products also, Infineon uses AI and uses in the manufacturing. To understand which areas potentially can benefit from AI, let's look at this simplified version of the whole chain of semiconductor manufacturing. So the core, let's say, areas are, first of all, design and development. Basically, that's where all the things happen on, let's say, paper, when you just come up with an idea how to produce a product. And to get a real product, you first have to get the base material from a supplier, in this case, for example, silicon. And when the silicon wafers are acquired, then they go first to the front-end manufacturing, where layer by layer in different processes, domain in this case also, certain layers are deposited. And I have to already at this point mention that every process can generate up to 1,000 parameters from one equipment. And if you have products, and there are products that require, let's say, up to 1,000 steps, you can imagine the number of the data generated weekly in such manufacturing. And once the wafers are manufactured and once the functional chips are finished, they would then be sent to backend manufacturing, where they will be splitted from each other, get into the small packages, so that we can connect the micro chips to the macro world of applications. And in this all process, which areas have already been proved to be successful using AI, or at least piloting AI applications? Some of them I have here. For example, technology and product development themselves are really beneficial when you use AI, because by that you can much quicker come to the market, much quicker you can bring your products to the market. Or let's say, imagine you can forecast in advance how much demand of particular product is in their market. So you can optimize your manufacturing process, your supply chain to meet your deadlines. But a big amount of these AI applications focus in manufacturing, and in particular for production process, for the quality, as well as for maintenance. So, for example, if you could automate some decision-making processes, or if you could predict some flows during the production, you could speed up significantly the whole process and get gain in efficiency. Or if, for example, you could get predictions when the equipment is going to get down, then you could in advance plan all your maintenance resources so that within the minimum amount of time the equipment is ready to go again, and you don't lose any time to produce a material. Also, very important inputs always can be received from correlation of the yield data, for example, after electrical functional test of the chips, together with the process, so that you know actually how your final product is impacted from each deviations during the process, or combination of deviations of the process. So we started, of course, piloting some use cases. That was around 5 years ago with big project for manufacturing, and all these learnings allowed meanwhile to establish a concrete flow of process how we conduct this AI in manufacturing. We use one process with 4 phases to transform the ideas into use cases, and at the end bring them into operations to gain the benefits out of implementation. So in the idea phase, usually we would talk to engineers and try to understand their problems, and with a little bit knowledge already what AI can do, what are the AI capabilities, one tries to link the AI solutions with the business problems. And once there is a good match, and once there is a first feeling of how successful this could be, then one would move towards the feasibility phase, where the first models will be built to see whether the data really give the outcome we were expecting. And once that is successful, of course, one wants to implement them in productive environments so that the benefits can be, the fruits can be collected. And it's important to mention that a majority of the use cases are getting really high value and high impact for the business when it's possible to scale them, scale across different domains, scale across different sites around the world. And with every use case, of course, during operations, it is still continuous learning process to understand what else needs to be improved and how we can make every use case even more successful. Another important aspect, what allowed us with time to get faster and better in conduction use cases, there was at an early stage realizing what kind of new roles AI is bringing with itself. Infineon is a semiconductor manufacturing company. It's not an IT company, but the necessity of having data scientists, data engineers, data analysts was integral part of the strategy that the company decided we need to build our in-house knowledge as well. And we have to have these people in interfaces between operations, technology, and analytics, so that the use cases can be realistically estimated in terms of feasibility and also, conducted in the best way. So in our case, usually each use case gets a dedicated core team with people from business, IT, and analytics to, find a solution and bring them to execution. But now some highlights, like finding really the needle in a haystack is the most challenging part of starting conducting AI use cases. And to drive them to success, first one has to ask who, how, and where should look for use case ideas. And let's go one by one. First, for who. Very important, I think, and very successful was for our company to dedicate people who from the beginning on started to serve as contact point between AI core teams and the domains. Often one can see that it's like two people, a data scientist and an engineer, equipment engineer, would talk to each other on the same language, but it seems like it's still not the same language. So McKinsey had an article where they named this role analytics translator. So basically you have to have an interface in between these two areas who could, with a bit of understanding from the domain itself and a bit of understanding with AI, try to make the links, try to bring the ideas and problems and the solutions together. So create some sort of role, as McKinsey calls analytics translator, or as we called it back then, use case collector, use case coordinator. What is important also that with time, upskill the people within your domains and also use the chance so that they can act as AI agents, that they can multiply their experience, their information within their communities, by that basically bringing a bit more feeling towards the staff, how AI can be conducted. And when you have these dedicated people plus the agents for AI, you can very quickly distribute the knowledge, what are the capabilities of AI, and also get the support to find the right use cases. So how to find these right use cases, as I mentioned, very, very important is that one understands what AI can do and should do, as well as what AI cannot and shouldn't do. Very often, of course, we are also having some cases where the conclusion is that no, AI cannot do it because of no data available, not enough data, not the right data are available, and this awareness must be always present. Very important is also in your house strategy, as also earlier mentioned, to develop and use standardized checklists to go through with the people to ask the right questions. Why this problem should be solved with AI? Are there enough criteria for this problem, like data, like benefit, like scalability? Is there enough reasons to start to put the efforts to put into this use case? Is there really no alternative than AI? Because very important learning was also with AI, one can do a lot, but does it really make to do everything with AI? A lot of existing systems, softwares, and standard statistical approaches can solve problems which is not worth to bring into the table for data scientists. Also, establishment of AI culture and awareness that AI is not going to steal the roles. AI is there to support, to enable. That is one important part if you want to the experts to come up and innovate with AI ideas. And of course, communication. Take your head out and look what others do, and also show a lot of examples. Finally, where to find these use cases? One is in every area that there is a need for improvement. Improvement means existing systems and existing knowledge cannot solve the problem. Automation. Automation means there is redundant work done by a human systematically every day and with high effort. There is high potential to apply AI. And finally, establishment of AI. Nowadays, we have experienced in manufacturing, there are some steps where processes were not established because either the infrastructure was not there or was too high effort and so on. Established to get new insights. As for the data, some inputs I have brought here that I like to share. Where to find the right data and what does it mean, right data? Once Clive Humby, a mathematician, he said, data is the new oil and it's valuable only when it is refined. The same way for our data strategy. If the data are raw and with bad quality, 80% of the time of data scientists go for only refining this data. So for that, first of all, there must be data strategy in place. The companies should make sure that in terms of data availability, quality, security, and usability, the infrastructure is ready. Second, the biography of your data. It's important to know why data are collected. Where is the source of the data? Who is using the data and for which reason? What happens if the data are not complete? And one also more important thing is how the data are captured. Because if the data collection process itself is not fulfilling the requirements for AI, you have to first make a step back, refine your data, and then go on with your AI strategy. Continuous visualization, monitoring of data quality with sometimes some tools, sometimes manually, is also a help to get insights about the data. And two tricks that I can tell based on experience is if the experts can very clearly, very distinctly explain or label data, then you are good to go to start with the proof of concept. And second, if you're in doubt whether the quality of your data are good enough, then give it to another colleague who has no idea about this data and ask to find the faults, ask to look for inconsistencies, ask to find some suspicious stuff. It always helps when the fresh eye looks at it. So I hope these tips and tricks could give you a little bit overview how we tackle our challenges on the way to AI journey, and for later maybe some other recommendations how to make AI journey successful. I will be more than happy to discuss and share in a fireplace chat.
Thank you so much. Super interesting. I really like the tip about saying explainability, right? Like of saying, you know, if the experts can explain the labeling strategy, then we should actually try to go. That's a useful tip. Yes, we also had like 2 questions coming in the chat. So I will start with Ashutosh again. Thanks for being so active. But the question of him is, do you face challenges in scaling the usage of AI models in day-to-day applications? How did you go about tackling this?
Scaling is even nowadays very challenging indeed. And the reason is mainly coming from technical reasons. It's about the equipment. So for manufacturing, at least I can say that it's equipment, old versus new, the vendor, the data. Some equipments have some data, some equipments do not collect the data. Indeed, this is even nowadays a challenge. Therefore, at least for our company, as I mentioned before, we agreed upon that on a large scale, we have to go for this optimization, standardization, and in best case, centralized data collection approach. Of course, here a management support is also required because it is an ambitious goal to achieve, but when achieved, it will have definitely very high impact on the business.
Makes a lot of sense. So I think we're very close to the last question, or to that answer from Ryan Metz. Another question: do you perform regular audits of your AI pipelines and models?
Well, to call it audit, I cannot say we call it audit, but in terms of implemented model, there is a dedicated IT team who is responsible for monitoring and the performance, both from IT and business side. Actually, business side is responsible to monitor in terms of the result. Do we have data drift? Is the model still giving the results we are expecting? In terms of IT, the monitoring means, is the model still giving at all results? Is it seeing, or is it assessing all the data? Are there any problems between all the connections in the systems? So, and in terms of pipeline, yes. So every local site has its own pipeline, which later is globally aligned and discussed and prioritized.
So I would say one more question, and then I would jump to the next talk. Watching time a bit, but this one is from Alexander Roth, who just spoke, and he is interested in what is your strategy around source of truth for the different use cases you identified? Data is not always easily available, needs to be prepared, and sometimes stored for reproducibility purposes.
Well, it's not possible to 100% say we do like this. It also depends a little bit, so additional aspects like availability of your staff and so on. Well, I can say as of now, we learned that when the data are not available, it's even not worth starting with feasibility studies. As I mentioned, in such cases, you just have to step back, improve your data infrastructure, improve your data quality, collect the needed data, and maybe the data that you haven't thought to collect, and only then try it again. I hope this answers your question.
I hope so. Otherwise, you can talk about it in the after event.
Exactly.
And we have some time scheduled there. Awesome. Yeah,
Exactly.
Thank you so much. It was super insightful, super interesting.
Thank you very much.
And this then leads us to the next speaker, Séverine Habert from Intel. And Séverine today at Intel leads a team that helps clients worldwide to deploy AI successfully. And before that, she did a PhD in computer vision at the TU Munich, and then worked on the Intel OpenVINO stack. And yeah, like even our team is impressed, or our team was impressed by a deep understanding of hardware considerations doing AI. And this is exactly what her talk will be today. And yeah, looking forward to it. The stage is yours.
Oh, so sorry, I was on mute. Can you see my screen?
Yes.
Let me reduce the chat. Okay, so I'm good. Okay, so hello everyone. So first, thank you, Asti and Intel Ignite for giving me this opportunity to discuss about so hardware consideration when deploying your AI model. So just okay. So my name is Séverine Habert. I'm actually based in Munich. I work since 4 years at Intel. I am an AI software engineering manager, and actually my team kind of helps is actually the bridge between the machine learning and deep learning developers. So we are the bridge between the developers and the Intel software developers, like creating the development teams. And yes, so we are ever working with what we worked for a few years with OpenVINO, the inference software for Intel, and also lately mainly also with the deep learning framework. So like I mentioned, I worked for a few years with actually OpenVINO, and through that and it was a quite successful project. And through that, I actually seen a lot of deep learning deployments. And actually, this talk, I want to say like the tips that I would like you to learn at the end of my talk about how to make your deployment successful. And so then let's start with a statistic from the Gartner Institute. So there's in one of the reports, they actually say that 20% of only 20% of the AI project actually make it to production. So there's a lot of ways that actually a AI project can actually fail along the development pipeline. So here I actually showcase the development pipeline here. So it goes from, of course, annotating the data. We heard that a lot from previous talks, like the data engineering part. So about the training your models, you train it until it's good enough for your application. And then you have the deployment phase where you will bring it to production, and finally where you will have to monitor the model. And actually today my talk is focusing on the deployment part. And yes, everything can go wrong along the way. But I think the deployment phase is actually quite underestimated. It also brings a lot of its challenges when you actually create a deep learning model, and this is why I want to focus. Really, deployment, as we should see it, is really the part where research actually goes to production and where it's actually face real life and its limitation. So as I will focus on deployment, I just want to have some understanding for everyone. So deployment here I refer to the fact to really integrate your machine learning model or deep learning model into an existing production environment. And that has really specific challenges compared to training. So first, it's not training that is performed anymore. It's mainly inference. I hope you all know what is training versus inference, but I kept the slides just before. So the training part is when you're training your model with learning the weights with annotated data. Inference is the part where you have like all the weights are already actually learned, and you are doing prediction on unlabeled data. And actually, even though training is getting a lot of focus and can be quite difficult to actually get your model to achieve good accuracy, it's actually in your model lifecycle, it's actually where a very short time of its life, it will actually the model will spend most of its time doing inference, because that's actually its purpose in the end. And therefore, between the training and deployment, there's big differences. So first is actually the environment where it will actually take place. They won't be in the same environment. So training actually typically happen in a research environment. So you have would be in the cloud instances or a powerful workstation. So, but on the other side, deployment can be actually anywhere. So it can be at the same place as training, of course, but it can be in a lot more, we say, wilder places, so closer to actually where the data can be produced. So that can be what we call more like the edge, so factory floor, home device, or security camera itself. So here, just a few examples. And of course, with environment comes this set of constraints that, of course, influence your choice of hardware when deploying AI. As not only the environment has an influence on how you should use the hardware, the use cases itself. So, for example, common use cases where Intel CPU are pretty good for training and inference. It's on very high resolution data. So it's typically like data like medical images, pathology images that are really big, or 3D data, because they are 3D, are also taking a lot of memory. Also can be also satellite images that typically won't fit on the GPU memory if you don't scale them, but if you're downscaling, you also come at a cost. So here, really, the type of data you have will also kind of dictate which hardware you should be using. And there's also the fact that there's not just your application, your AI application is not just isolated. It will run alongside other applications. So typically, it could be video streaming. I mean, your data is coming from somewhere. It has to be decoded. You also have the display also can be happening. And that you have to kind of think, do you need the extra hardware for that? Or can your application can run alongside this? So this application already running on the device you plan. So this is what you have to kind of look. So here's about the use cases. So from the environment plus the use cases, you're dictated by that through like a lot of constraints comes to your application. So here I just have a little sample of the constraint you can have based on your deployment environment and use case. So you have like then requirement comes about throughput, size, cost, accuracy, of course, response time. There's a lot. So here I just translated through to what we can measure actually, so metrics. So cost, it's a very generic word. I mean, I think in more business, we will call it like a total cost of ownership, like the purchase price of your actually hardware, plus thinking the cost of operation. Size can refer to multiple things. So that can be the size of the neural network in memory, for example, or it can be the size in the production environment itself. So at Intel, we call that mainly a form factor. So really had physical space of this device. There's also power consumption that can be measured by the power that can be measured by power consumption. So that is measured in watts typically, and it's also up to you. Do you want to measure it just for the accelerator, so the device you attach to which you want to accelerate your AI? You attach to a host, or you can also measure a host and accelerator, for example. However, what I've seen the most as the metrics that people must the most is actually most the time performance one. So there's two. There's one that we refer to how fast your application goes, so what we call typically throughput. So in Vision AI, that is often measured as frames per second. And the second one is latency. So this is how fast you will get actually your answer. And those are actually interconnected and often quite opposed. So in deep learning, you will often find that to have a low latency application, you might require to have a low batch, even typically one, as you would just do the inference on the image incoming, so batch one. While for a neural network that to actually often perform better in terms of throughput, yeah, you actually need a higher batch. So this is actually often quite opposed. So it's a question of compromise. And so from here I kind of showcase like some not exhaustive, I would say, metrics about that you can have about your deployment. However, but in the end, it's not just about the metrics, but the numbers you will measure with those metrics, and your environment will actually, and your use case will actually give you constraint that will give you like a lower and upper bounds to which you will be limited, and those bounds will actually give you your space of possible hardware. So here I just wanted to take an example where I took one of the metrics, like the power consumption. And here I kind of showcase with the Intel hardware. So for example, we have like some Intel Movidius chip that is so we have the Intel Movidius chip that is like 2 watts, for example, which is really for embedded cases, and it goes like Atom CPUs. There's also 15 watts. So this that goes really increasing. And so this GPU, they can be really more energy side. And of course, based on that, you will have not at all the same. Depending on the application, if you are really going embedded, you will have to really focus on those kind of hardware. While if you have not so restrictive environment, or even if you just don't care, you can also just go bigger environment. And that is just for one metric. As you will really have like your multiple metrics, cost, power, that will reduce down a lot your choice of hardware. And actually, that makes me want to bring to my other main point. One of the points I want to bring here is, while instead of trying to just try to fit your model to the possible few choice of hardware that you have, because of all your metrics cannot define, we have really a small pool. The question would be, how can you actually, from the beginning, try to also get your model architecture to actually also be put in the loop to be put in the loop from the beginning, such as at the end you're not find yourself in a mismatch. So it's actually a mismatch. I want to bring my experience here. So we that I've seen several times. So we have this that I already mentioned, this Movidius chip that is that you can find also included inside a USB stick that you can basically do inference on your laptop using that. And often it's a really great. It's 2 watts. It's really, you can't beat that in terms of performance slash on the performance power consumption ratio. However, it has a limited memory, and we had we had few customers that come and say, "Oh, I have this instance segmentation model or an object detection model," and they took the biggest one that they could find, that really a really big model with because has really high memory footprint, and it would just not fit the device because yes, the model is really too big for the deployment the hardware they were targeting to. And though in the end they haven't had to have to change the deployment hardware, but that comes of course because that it might be not even as embedded, so not as low power as what they were targeting at first, or they have to go back to change the model architecture. And that is like, you're already at the end, you don't want to have to go back to training. And I think that is coming from the fact that you should really have model architecture and deployment from the beginning. So I will go back to that. How important can model architecture is to fit your different deployment metrics. So here I have like a graph that showcases actually for throughput, different architecture with like same accuracy. So for example, here you take like ResNet and you compare like a DenseNet 169, you have same accuracy, but ResNet is like 3 times faster. This is for throughput. And here for model complexity, which often you find as a giga flops. And there's actually the ratio can be really more important. So efficient net, which is a family of model, really, really efficient, as his name saying, is like, I think it's 10 times more, it's less operations than the ResNet 101. And that really makes that your, depending on how you choose your model architecture, can make your model, your application viable at the end when it's about to deploy it. And here actually come my tips really that I would like to share with you today, that it's really your choice of model architecture should really be, you should really have it in mind from the start, and even knowing from the start what will be your metrics and your bounds, or really knowing from the start of your project your deployment environment. And it's not just knowing roughly how it will be, for example, in the factory, but really knowing in detail what will be your power consumption, the size, or even even better, knowing what would be the hardware, or at least the small pool of hardware you will be running on. And that will really help you to have like a realistic expectation and not find yourself in a dead end when you're about to deploy. So really my first recommendation would be really to have like a test setup for deployment even before you train, such as you really can just train and deploy almost immediately to really have like a good feedback loop. And also you can also just use what I call proxy models. So you can benchmark on your closest pre-trained architecture on your test setup that you just had created before. So even before training like this, you can at least know, okay, this architecture kind of performs good enough on the test setup. Or is it always way too slow? No, just discard it and go to another one. And like a trap I've seen several times the customer doing is often that to really go for the state-of-the-art model for the use case, which is good, and it's often deep learning is really driven by innovation and the research, and I completely understand why you want to take that. But often the problem is that the research is mainly driven by one metric, the accuracy, but don't really care about the rest. And so I think it can be the trap here. So maybe it's not just should really look at the model architecture. Maybe goes for less innovative models, but at least go for everything that is really good enough in your constraints, even if it maybe means losing a bit of accuracy, but at least it will fit all your metrics for deployment. And I just want to finish on the slides that what we are doing at Intel. So for software, we are trying to develop actually software that even have tried to span above all these different hardware consideration to have like unified API, such as you actually don't have to kind of dig in every hardware. So we have, for example, frameworks, but you can do that on CPU and GPU. We also have, so I mentioned working on OpenVINO. So basically all the hardware you could see on this power, the power increasing line that I showcased, like arrow I showcased, it was supported by OpenVINO, and it's just one API to actually to run that on all the different hardware. And also maybe another consideration for doing acceleration for inference and the deployment. There's also a lot of techniques where you can do model compression, like quantization, pruning, and knowledge distillation. That is actually included into the Intel neural compressor. So this is more like software techniques where you can to help you deploy to improve your deployment inference. Okay, so I had the slide. Okay, so I think if you have any question for me, I can take it now. So
thank you so much for that. Very, very interesting talk. It's always a good good framework, good framework with the different considerations. Yes, so thanks. Ralph is asking a question. So I would actually only do this one question as the presentation went a bit over time. But the question from Ralph is, first of all, thanks for the presentation. As all of the metrics, latency, power, and so on are influenced by both software and hardware, the selection of an appropriate setup can get quite complicated. Do you have any recommendations, or is there even a guidance on how to approach this problem, select the right setup?
Yes, I mean, I think it's mainly first you really have like I kind of showcase the framework you have to do now. It's like you really have to look at the use cases first, and then you have to look at where it will be. So you can, I think it's kind of hardware first for the deployment, and then you can kind of look at how the software can help you on top of that. After, at least my experience is like I always people ask me which hardware should I use for this use case, and it's like there's no just one magic number, and I think there's no like pure guidance on for this use case you should do that. And I think it's mainly it's about discussion that you should always have about And of course, for different domains, there will be preferred setup. But so I hope I think the answer is like there's no magic. Like, unfortunately, that would make my job a lot easier.
Fair enough. So, right, then with that, I would actually go to the last speaker. As I said, we already ran a bit over time. And so to not keep the guests longer as we promised. And the last speaker will be Julia Gong from Stanford / Microsoft AI. And Julia is an old friend of Hasty, and it's always great fun to chat with her. She was one of the early users of Hasty back in the day. And we met her when she was doing her undergrad studies at the Medical AI Lab in Stanford. We were working with one team there. And yeah, as I already teased her today, like today, Julia works at Microsoft AI, while she's still pursuing research at Stanford as a joint lecturer. And yeah, she works also together with the Institute for Human-Centered AI. It's one of the leading institutions, I would say, in the world that does research and how can we actually apply all of the nice things we do to the real world. And she will dive deeper into a framework she developed how to do that for medical use cases. And I had a sneak peek at the paper, and I think it's also relevant for much more verticals than only healthcare. So excited to share the screen.
Awesome. Thank you so much, Tobias. Let me share my screen. All right, so hopefully if that worked, you can see my screen. Yeah, so thank you so much for the generous introduction. It's been really wonderful to watch Hasty grow over the last few years and really start to pick up pace. So I think this is a really great event that sort of encapsulates that vision of taking ML to industry and really letting it fly. So yeah, as Tobias mentioned, I'm going to be discussing sort of this recent work from last year that I worked on as part of my master's thesis research at Stanford for 4 human-centered AI principles for bridging this AI to clinic translational gap. And this is sort of specific to the medical AI realm, but as I'll sort of discuss, these principles are actually probably more broadly applicable than just to the medical domain. And I think they play off well to a lot of the points that the other speakers have discussed today too. Yeah, so this was part of the Kai workshop last year. So I did want to give just a really brief overview of where I'm coming from. So this is sort of a summary of the sort of work that I did during my master's thesis. So I actually don't really come as much from a human-computer interaction kind of background. My background is in computer vision, and in my master's, I primarily worked on applications to general computer vision and also to the medical field. So a couple of the works I worked on were for nerve tissue segmentation, for which we actually used Hasty to label the entire data set, and the work in video object segmentation. As I was working on these different works, I sort of craved understanding, how would these works really play out in the real world, and what is maybe stopping works like these from making it into industrial applications or into applications that actually touch the hands of users. So as I began thinking more about that, then I became intrigued by, what are, from higher level, zooming out of the code that I was working with every day, what is sort of stopping this from happening, and what are the kinds of measures that we can take or considerations that we can think about that sort of influence that. And so that's sort of the motivation for this work on the human-centered AI principles, and really taking a step back and thinking about what are some blockers and potential solutions for these different issues that I'll be talking about. Yeah, so I just wanted to also thank my co-authors in this work, who are amazing advisors to me, Drs. Karano, Serkin, Young, and Holsinger at Stanford. So some motivation and common ground, and why we're all here. Despite these sort of great innovations in medical AI methods, or maybe AI methods in general, there sort of exists this translational gap between medical AI methods development and actual deployment of these methods into the clinic. And so the question I wanted to ask is, what can we do to bridge this gap? And specifically, from the standpoint of being AI researchers and engineers who are really involved in sort of the active development of these methods. So some common struggles of medical AI methods development, maybe this will sound familiar to folks who are in the medical field, and some of these I think are also applicable widely outside of the medical realm. But for example, there might be situations where there are folks who are working on this exciting medical AI method, and they're like, oh, this is a cool method I create. I'm really excited to try it out on X-ray data or something like that. And then maybe if they talk to someone who's in the medical field, one of the complaints that might come out of this conversation is, that's all great that you have this cool method, but it really actually isn't targeting important needs that we currently see in radiology. And so this is sort of one of the examples of methods first thinking, or thinking about technical novelty instead of clinical need. In addition to this struggle, there might be others such as information silos. For example, why is it that physicians are hesitant to use an AI system that was built? Oftentimes it's because of this limited information exchange between the technical team and the clinical team, not discussing how the technology works, or its limitations, its intended scope, possible mitigations to errors that will come up. And so this really sort of clear communication about the limitations of the work and things to watch out for, how to use it, intended purpose, is really critical when especially in working in high stakes domains like medicine. Another issue that sort of ties into that previous piece is low collaboration and consistency. Oftentimes, I think in different ML applications, one of the things at the start of the project is like, okay, we have this idea for what to do. Now, all we have to do is just get the data and we can hit the ground running. But especially in medicine, and also, you know, for other applications, that really is the painful part. The painful part is getting the data, is getting that properly annotated, clean data that is also representative of the situations that we would want to see this deployed in the wild. And especially in medicine, also another hurdle is that no one really likes to share their data. It's sort of an asset to have this privileged access to this data, especially when there are a lot of different regulations, and rightfully so, that accompany the medical setting. And so often when thinking about medical AI tasks, aside from very few benchmarks that are currently available in the wild, it feels like we have to build those data sets from scratch ourselves. And as I mentioned, right, like for one of my thesis projects, we had our images, but we had no annotations, and there were no similar tasks out there in the wild. And so we had to annotate it ourselves. And that's sort of this common theme that sprouts from many different sort of medical AI applications. And finally, for another sort of key hurdle here is slow iteration and monitoring. Often we'll, after working on a project for a while and doing a lot of fine tuning of the model, and everything seems to work well on the held out set, on the test set. And then the next step, of course, is to think, well, this is a great technology that we just made. Maybe we can test this out in the clinic. And the issue in medical AI is often that'll take a really long time because of all sorts of regulations and concerns for patient safety and data privacy, all of these different considerations. And in addition to and even putting these aside, even if we are able to sort of jump over those hurdles, how are we going to monitor this model or this technology over time? As the data changes, as the scenarios change, how are we going to be able to monitor it in the wild so that it's actually continuing to work as it was intended to? So that's a really key piece as well when thinking about deployment of medical AI methods in the wild. So all of these different frictions are going to widen this gap between AI methods and clinical deployment. So the question is, what can we do to slightly keep this gap smaller? How do we stay aligned? So this is sort of the motivation for NICE, which is an acronym that stands for 4 different human-centered AI principles that we propose in this work for translational medical AI research. And these are derived from examining different case studies in the literature and also from our own experiences. So NICE stands for needs-focused innovation, or needs, iteration, collaboration, and error prevention. So I sort of tried to formulate this in a digestible way into 3 key components for each of these principles or pillars. The first is, as we identified earlier and alluded to, what is the problem? The second is, what are some long-term ideal picture kind of goals for solutions to these problems? And then in the near term, what are some short-term actionable proposals that we can use to start addressing these problems and moving the needle toward those ideal solutions? So as mentioned earlier, for each of these pillars, the problem for in the needs pillar is many efforts currently are targeting this idea of technical novelty over clinical need. And that's often leads to wasted efforts, or maybe interesting efforts, but efforts that at least won't make it into in deployment in the wild or into industry. Iteration, it's hard to rapidly test in these technologies in real high stakes environments due to a lot of different barriers that we've discussed briefly earlier. Collaboration, there are information silos both within and between the technical and clinical teams that are collaborating in order to make medical AI development happen. And that is sort of termed as intra and interdisciplinary collaboration, which we'll go into. And then finally, for error prevention and monitoring, there are a lot of different issues that pop up in the wild when you're done testing on your single held out test set, right? Like this data distribution shift, model brittleness and robustness and bias. And in addition to this, there isn't necessarily a standard for how to monitor these models after they're deployed in the wild. So these are all pretty big idea problems. What are some of the big idea solutions for these problems? So some ideal solutions here, and these are sort of, I tried to make these concise as like really snapshots from the paper. I can also share the link later to the full paper, but these are trying to encapsulate maybe the main ideas. So we're leaving out some of the smaller details and examples. But for needs-focused innovation, the ideal solution is we would like to align our incentives and orient medical AI researchers towards a more needs-focused approach toward their work. For iteration, this means ideally we'd like to have these playpen environments that are integrated into clinical centers that would allow for this continuous deployment kind of testing of different versions of the algorithm as they're being developed on real world data, so that we can anticipate what's going to happen and really plan for those real world scenarios as we're developing the technology. For collaboration, well, more collaboration. And this is, sort of a obvious and maybe a way to avoid the actual question of what is the problem, but we really do need more collaboration both in between the technical and clinical teams, as well as within these teams themselves to make sure that they're up to date. So I'll go into this a little bit further when talking about these short-term actionable proposals. How are we going to create more collaboration? And finally, for error prevention and monitoring, ideally, right, we would like to have these models that are unbiased, explainable, robust. And at the same time, when these models are deployed in the wild, we would like to have continuous model monitoring systems that sort of allow us to monitor and gauge the performance of these models as they're being deployed in real world situations. So what are some things that we can do in the near term that can move the needle toward these goals? So for some concrete proposals for needs-focused innovation, a couple of examples of things that we propose in this work. First is to have needs-first incentives in publication venues and funding. This is sort of in thinking about what are the incentives in the academic world. We want to be sort of having high impact of our work, reaching lots of people and sort of being able to share these ideas and move the field forward. And so that means, if we're able to establish more high impact domain specific publication venues that really prioritize and highlight needs first work, that would really help to sort of align those incentives for researchers to be willing to pay more attention to the needs first kind of way of thinking and also do work in this area. And this is really important for sort of starting to reframe, and especially in applied research, to reframe from thinking about technical novelty into thinking about needs first. Another sort of idea along this line of thinking is the allocation of positions and funding and resources to needs first work. And this may come in the form of funding through grants or funding through different university researcher positions. These are all ways to sort of try to show, put your money where your mouth is, really show that we're interested in these first kinds of work and we're willing to allocate the resources for it. And then this next piece of deep collaborations is also really important. When one of the things that I noticed in my work, and I'm sure others have also noticed in your work, is when working in applied research, it's really important to have that strong communication with domain experts. And from the technical side, you just can't know everything about what's really happening on the ground and what the true needs are. And so that's why it's all the more important to be having these deep collaborations with people who are familiar with the domain, to understand what are the needs, right, in needs first. So that goes into this collaboration pillar as well. So it's really important to involve the clinical teams and other relevant stakeholders in these conversations as these methods are being developed. The next piece for iteration, short-term proposals, I sort of divide into two main camps, and these sort of draw inspiration from actually the autonomous vehicles industry in thinking about how AV has been really successful in developing these exciting, AI applications for navigation and for other applications on the road. Thinking about what were some of the ways that they were able to tackle not being able to rapidly test in high stakes environments all the time, because the common thing between medicine and AV is that the real world situation is very high stakes, but we really would like to ideally be able to test before actually heading into the real world. So the two main things here for short-term proposals are realistic data synthesis and high fidelity simulation environments. Developing realistic data synthesis methods is really thinking about ways that we can develop synthetic data that can alleviate that bottleneck of having realistic data from the wild that will enable our different applications. And high fidelity simulation environments is trying to sort of replicate these environments in a contained way before these methods are deployed into the clinic or into whatever real world situation. And this is sort of to avoid that bottleneck of not having these playpen environments in the short term to integrate into clinical centers and work with real data. So efforts that really try to tackle synthesis of realistic data and at the same time simulation of the environments that we expect in the real world are really key. Some other examples of methods that feed into this might be refining human-in-the-loop approaches for these methods so that they don't have to necessarily be automatic, but they can at least include that domain expertise from the different stakeholders that are involved, such as physicians, clinicians. For collaboration, there are sort of two pieces, one for interdisciplinary collaboration and the other for interdisciplinary collaboration. For interdisciplinary collaboration, it's really important to actively cultivate these cross-disciplinary teams by addressing the incentives. And there are sort of sometimes competing or at least not completely aligned incentives when thinking about the different stakeholders and that could be involved in any AI project, but especially in medical AI. And so that's why it's really important to establish trust between the teams that are working on the technical side and on the medical side. In addition to interdisciplinary collaboration, it's also really important to have a systematic way to accumulate knowledge within the discipline. So that's within the technical team on the AI side and also within the medical team. And currently on the AI side, which is what I speak to a bit more because I'm coming from that background, there is this sort of lack of systematic knowledge accumulation in medical AI specifically. We have these really good examples of benchmark data sets and other really systematic ways of evaluation and all of these sort of toolkits that are created in maybe general AI or even general computer vision. But for medical AI in particular, there are still not very many benchmarks across a wide variety of tasks that are of interest to the community. And there aren't really as many efforts to do sort of open sourcing of these different approaches with respect to those benchmarks or standardizing documentation for data and code. Things can be really left and right and not centralized. And so really encouraging data and code sharing and incentivizing open science efforts so that this knowledge can accumulate over time, which is one of the reasons why the human species is so successful, is having that knowledge accumulation over generations, can really speed up that progress for interdisciplinary collaboration, which will then in turn benefit these interdisciplinary collaborations in medical AI. And finally, from error prevention and monitoring, it's with the short summary for this bias, explainability, robustness area is really continuing to do basic and applied research in these areas. And that I sort of break it down further in the paper, but there are a lot of different specific areas that are of interest in these domains that can be applied in the real world if we just take it a step further and really think about how specifically can we apply these methods to the medical AI setting and in deployment. So it's again sort of thinking about how do we encourage that domain focused kind of approach to thinking about these different challenges. And finally, standardizing compliance metrics, measures of model confidence, these different evaluation measures that we think about for monitoring the model in deployment, and really developing standard toolkits, standard, like easy packaged up and standardized ways of measuring the model performance or confidence or whatever other measures that are going to give insight into how the model is performing in the wild. To really establish those standardized toolkits for use in the wild is really critical, as well as taking inspiration from how development works in industry is continuous model monitoring pipelines, having reliable monitoring tools that automatically report or allow for manual inspection when different metrics are slipping, and developing more efficient workflows for frequent and reliable code changes and integration into the real world environment to enable that rapid iteration. This is sort of a high level overview of these pillars, but hopefully that gave a good overview of what this is sort of trying to tackle and some examples. The takeaway that I really want to say, especially to our audience here today, is these are 4 core guidelines for medical AI, but they can also be applied to other disciplines. And I hope that it's clear how these different concepts can be abstracted, taken away from a specific domain and really thought about in the ML in the real world context. Please also stay tuned for a more comprehensive work that sort of covers these in more detail. Currently, it's under submission to a journal, but we're working on getting that out in the real world as well. So thanks a lot for your time and looking forward to the Q&A.
All right, super cool. Thank you so much. It's really interesting work, I believe, and actually would be interesting how you can back that up with data. But yeah, then we need to read the follow-up. Read the journal once it's published. Yes, like in general speaking for the event, so we ran a few minutes over, so sorry for that, but I think it's not too many minutes. And we would actually not do the big Q&A with Julia right now, but we move that to the fireside chat so we can all have a break as planned. And yeah, would now do essentially a few minutes break. And for the ones that are in the fireside chat, like you will be assigned to breakout room, you don't have to do anything. And for all of the other ones, you still can ask questions to Tristan and some others of the team. And yes, thank you so much for attending. I hope you enjoyed it. We will send you the recording of the event again tomorrow in the follow-up email, then also like some highlights and some summaries. And would love to hear your feedback, your thoughts. If you want to just talk to us about what we do, and you can always reach out. And yes, thanks again for joining. And see you next time.